Okay, we're going to go over section 4.1. I just want you to copy down the answers as much as you can. And this section deals with identifying linear functions. You're going to see tables, graphs, and equations. Sometimes the tables are going to be in the form of coordinate points. The graphs there'll be various types of graphs, and the equations could also come in the form of functions. Now, what you need to realize and point out is what elements or what do you look at or look for whenever you're dealing with tables in order to tell whether or not it's a linear function. What do you look for when you're given a graph, and then what do you look for when you're given an equation or a function? And here are some of the things you should look for. On this one, on this particular page, here are the answers. Notice that this first part, it was a graph, so we looked to see if it passed the vertical line test, and then it must be a straight line. All right, so here are the answers. I've already gone over these in class, so you can copy them down as you wish. The next part, I'm going to go to the coordinate points. With the coordinate points, if you notice, they had to have a constant rate of change. So you had to look for the change in y over the change in x, and they all had to be consistent. For instance, let me go ahead and erase this part. Let me erase this. If you notice, it could be -2 over +1, -2 over +1, the change of -2 over the change of +1. All of these are consistent, so they have the same rate of change. All right? And that's what I want you to look for. The other thing I had you do was change something into standard form. So notice we got the x and y on both sides. And then I asked you to graph it. So I basically used y equals x minus 4. I put a dot at -4, and then I had a slope of +1. So up 1, right 1, up 1, right 1. And then on the one down here below, the very last thing, it gave you the function of y, or f of x equals 2.5x. I started out at 0, 0, and I just created some points right here and then plugged them into the equation right there, and the output was what was follows. So 0 times 2.5 is 0, 1 times 2.5 is 2.5, so on and so forth. Then I graphed the coordinate points. The domain happened to be all of these numbers, between 0 and 12, and the range happened to be from 0 to 30. And the reason I chose this way to represent it is because the snowfall can go anywhere from 0 to 12 hours, or even the amount of snowfall is from 0 to 30. So it would include all those amounts in between. On this section, you just had to determine whether or not it was a function. Number 1, yes, it is a function, but it's not linear. Number 2, it's not a function, and it fails the vertical line test. Number 3, basically I gave you coordinate pairs. It's not a linear function because the ratio of change in y over change in x, so this would be 3 over 1, this would be 5 over 1, and this is 7 over 1. All of those do not equal, over -1, they don't have the same ratio. Whereas if you look at B, they all had a ratio of 2 over 1. -5 to -3 is +2. -3 to +1 is +2. And then the x values increased by 1. They all increased by 1. So the change, it was a constant rate of change, therefore it was a linear function. On number 4, here's the graph. Y equals -2x. So I start out with 0, 0, because 0 times -2 is 0. And then I went down 2 to the right 1, down 2 to the right 1 to graph to the next points, or up 2 to the left 1. And then I put it in standard form by putting x and y on the same side. The last part, basically, y equals 5.25x is the function we dealt with. I just made some 0, 1, 2, 3, 4, 3, 4, and I even jumped all the way up to 15, since we are talking about estimated the Shabelle River in Somalia rising. So basically, this was over time, so we're talking about hours. So in 15 hours, it would have risen 78.75 inches. So the domain, a reasonable domain, would be anywhere between 0 and 15. Actually, it could even rise for even more than that. And there's another way you can do that. And then, of course, the rise would have been from 0 to 80, or approximately 80, and it could keep rising. On this page, number 1, it's linear, but it doesn't pass the vertical line test. So if I were to draw a line straight down, multiple points. This one is not linear, but it does pass the vertical line test. On this next section, number 3 and number 4, notice what I did. Set A had a constant rate of change of 1.5 over 0.1, and the change in y over change in x for all of set B was not the same, therefore it was not a linear function. Number 4, I started out at plus 3, and let me blow this up a little bit. Okay, if you notice, I started out at plus 3 because that was my y-intercept, and I went down 1 to the right 1, down 1 to the right 1, and that was the slope. Okay, let me go ahead and get back to this. Then on number 5, and then I put it in standard form. I just moved the x over by adding x, and I got x plus y equals 3. On this right here, a campground charges $30. Well, it's good. If you notice, let me blow this up a little bit. All right, here we go. The campground starts off with $30, and then it's going to increase $4 for every person. So I went up 4 to the right 1, up 4 to the right 1, up 4 to the right 1. So 0 people would cost $30. 1 person would cost $34. 2 would cost $38. 3 would cost $42. I didn't put it down, but I could. So 3 people would cost $42, and so on and so forth. Notice, just like I told you with the Somalia River, it could have gone more. So I could put ... and then close the brackets. This means it could keep going on. So if it keeps going on, I do the same thing over here. So these are corresponding values right there. But I also put the ... because it also could increase. Because when you're at a campground, who's to say how many people can fit at a campground?